In this example, we are going to consider the following subset of R3. S will be the set that is comprised of the vectors 1, 2, 3, 4, 5, 6, and 7, 8, 9. Notice my intense level of creativity in creating those vectors. We'll pose the question, is S linearly independent? And if not, we are going to create a minimal spanning set. So for the record, a minimal spanning set is a proper subset, well, sometimes proper subset. It is a subset of S that has the same span as S, where the minimal spanning set is also linearly independent. So the question that we need to pose here is, if it's not linearly independent, then which one of these three vectors can be expressed as a linear combination of the other two? Usually that's not done in a unique fashion, so allow me to explain. So first, we test for linear independence. We'll refer to these three vectors as being the vector v1, vector v2, and vector v3. The test for linear independence states that we'll take a linear combination of these three vectors and we'll set it equal to the zero vector in R3, and we'll see if this has more than just the trivial solution of C1, C2, and C3 all being equal to 0. Now the shorthand version for how we do so is we set up a matrix with three rows since we're in R3. The first column will be the first vector, 1, 2, 3. These represent the coefficients of C1. The second column will be 4, 5, 6. That'll represent the coefficients of C2. And then the third column will be 7, 8, 9, and that'll represent the coefficients of C3. We augment with whatever these things happen to be equal to, and that is going to be the zero vector. We are then going to take this down to reduced row echelon form, a feat that we could probably do by hand, but for the purposes of saving a little bit of time, we're going to do the graphing calculator version. So first, enter the matrix menu, arrow over to edit. We'll go ahead and just edit the first matrix that's in here. We'll do a 3 by 4, and then we'll insert these rows exactly as we see. So 1, 4, 7, 0, 2, 5, 8, 0, and 3, 6, 9, 0. We'll quit out of this menu, re-enter the matrix menu, and select matrix A just to make sure that everything got loaded into the matrix correctly. Then, once more from the matrix menu, we'll select reduce row echelon form, select our matrix A, and ask the calculator to put it into reduced row echelon form, which it does so without complaints. Now from the first row, we are seeing 1, 0, negative 1, 0. The second row says 0, 1, 2, 0. And the third row states 0, 0, 0, 0. Now to give an interpretation to this reduced row echelon form, the first row is telling me that C1 minus C3 is equal to 0, and that C2 plus 2 times C3 is equal to 0. The third row tells me the very interesting fact that 0 is, in fact, equal to 0. Thanks, third row. You're a big help. Now, the interpretation that we can give to this is because there is a free variable in the form of C3, the leading ones are associated with our lead variables, and anything else would be our free variable. So because there is a free variable, that's how we can tell that the system, that this set is linearly dependent. Set is linearly dependent. Now, the existence of a free variable lets us know that one of these vectors is redundant in the sense that it can be expressed as a linear combination of the other two. Anytime you have a vector associated with a free variable, that is the redundant vector. So what we're going to do is set C3 equal to 1 and solve for C1 and C2 in terms of those. Then we'll explain what to do with it. So let C3 be equal to 1. Then according to these two equations, this tells us that C1 is equal to 1 and that C2 is equal to negative 2. So the idea behind doing this is we'll take these three values, plug it into this equation, and set up the following. This lets us know that 1, 2, 3 minus 2 times 4, 5, 6 plus 7, 8, 9 is equal to the zero vector. In fact, let's go ahead and verify this real quick. For the first component, 1 minus 2 times 4 plus 7, that is in fact equal to 0. 2 minus 2 times 5 plus 8, that's 0 for the second component. And for the third component, 3 minus 2 times 6 plus 9, that is in fact equal to 0. The idea is whatever we had associated with the free variable, we can now solve for as a linear combination of the other two vectors. We do this by adding or subtracting where appropriate the vectors over to the other side of the equation. So we'll add 2 times v2 and we'll subtract v1 from both sides. So this means anytime I set up a linear combination of v1, v2, and v3, I can actually set it up as just a linear combination of v1 and v2. This makes v3 a redundant vector. So as far as the minimal spanning set is concerned, we can remove, and we're going to call this S prime. We're going to remove 7, 8, 9, or vector v3, from the set. This means that the span of S is equal to the span of S prime, and S prime is linearly independent. The reason that I know that it's linearly independent is if I were to go back to the test for linear independence, we have now removed the third vector. So in reduced row echelon form, this column would not be present. And with that column not present, I am seeing C1 is equal to 0 and C2 is equal to 0. Sorry about all those shadows that I'm casting right now. It's just a lovely time of day. So this is the process of creating a minimal spanning set.